In this lecture, we will look at a proof for Lebesgue's differentiation theorem in R, which was stated in the last lecture. So it says, let me recall, it says that if you take an absolutely integrable function on R, and if you define its associated integral function capital F, which is the integral over the interval minus infinity to x of ft dt, then this integral function is first continuous and then differentiable almost everywhere in R, and the derivative is equal to the original function fx almost everywhere in R. So we have already shown that this is continuous in the last lecture, and we will continue our proof and take care of differentiability almost everywhere in this lecture, which requires substantially more work than continuity. So let's look at the proof. So I will follow the proof outlined in Stein and Shakarchi. So I will follow their method to prove this result. So the first step is to note that it suffices to show that for any alpha greater than 0, the set E alpha defined as follows. So this is the set of all x in R such that the lim sup as h goes to 0, 1 over h integral x to x plus h ft dt minus fx, and you take the modulus of this, is greater than 2 alpha, has measure 0, because this would imply that E0, which is the set of all R such that set of all x in R such that the lim sup h goes to 0, and the same expression as before, x plus h ft dt minus fx is greater than 0 is nothing but the union, countable union of E1 over n in n, and since each has measure 0, then it would follow that ME0 is 0, which means that these two things are equal as limit h tends to 0 almost everywhere in X. So it suffices to show this for this set E alpha that it has measure 0. So M E alpha is equal to 0. So let's try to see how we can show that M E alpha equal to 0 for any alpha greater than 0. So for this, let us fix alpha for the rest of this proof, and let epsilon greater than 0 be a given arbitrary number. Now we know that the compactly supported continuous functions are dense in L1 functions. So there exists G in CCR such that, so for this given epsilon, there exists G such that the L1 norm of f minus g, L1R, is less than or equal to epsilon. So this we have already seen that the continuous compactly supported functions are dense in the L1 norm, and so we can choose this G for a given epsilon. And now if we write integral 1 over h integral x plus h ft dt minus fx, now I am going to add and subtract some relevant terms, ft dt minus 1 over h x to x plus h gt dt, then I have to add again 1 over h x to x plus h gt dt, and then again I am going to subtract gx, so minus gx minus fx, and then again plus gx, so I am putting it in a bracket with the f minus f, so it becomes minus. So I am plugging in these two terms, 1 over h integral gt dt over x to x plus h and gx. So now we know from the first fundamental theorem of calculus that we saw in the last lecture, that the limit as h tends to 0, 1 over h integral x to x plus h gt dt is equal to gx for all x. This is in the, so I can take the support of G as the compact set on which x can move, or I can take some interval a b which contains the support of G. So this is a compact set, so you can always have a finite length interval a b which contains this support of G. So on this set we have this, that the limit as h tends to 0, 1 over h integral gt over x to x plus h is equal to gx. So the term in the middle, if you take the lim sup on both sides, the term in the middle is going to vanish, because this is the same as taking lim sup as h tends to 0. So this is going to be give you 0. This whole thing is 0. So we are left with these two terms. So we will deal with them separately. So we see that lim sup as h tends to 0 modulus of 1 over h integral x to x plus h ft dt minus fx is equal to or rather is less than or equal to the lim sup as h tends to 0 1 over h integral x to x plus h ft minus gt dt minus fx minus gx. And now another application of the triangle inequality will give you the lim sup h tends to 0 1 over h integral x to x plus h modulus of ft minus gt dt plus, so there is no h in this one, so you simply get modulus of fx minus gx. So we get this inequality. And now if we denote for a function f in L1 of R, if we denote mf, this is again from R to C, which is a function defined as follows. So this is the supremum as h tends as over h greater than 0, 1 over h integral x to x plus h ft mod dt. So this function has a name. This is called the maximal function of f, and it is something like a supremum over all the average values of that f takes over over intervals containing x on the right hand side. So only right handed intervals containing x. So if we have this, then we can we can bound the first term, which is lim sup as h tends to 0, by the supremum as of h greater than 0. So this term here is bounded above by the maximal function of f minus g, because we are taking the lim sup as s goes to 0, and this is less than or equal to the supremum over all h greater than 0 of the same expression. So for this maximal function, let us write first what we get. So we get lim sup h goes to 0. So again all these h goes to 0 that I am taking should be from the right hand side. Okay, we can also use the left hand side, but let me just take the right handed limits. Everywhere I'm going to take the right handed limits. So with this the maximal function, so I get this inequality 1 over h ft dt over x plus h minus fx modulus is less than or equal to m f minus g at x plus modulus of fx minus gx. So now if we let f alpha to be the set of all x in R such that the maximal function of f minus gx is greater than alpha, and g alpha is the set of all x in R such that mod of fx minus gx is greater than alpha. So now we note that if x belongs to E alpha, then either x belongs to F alpha or x belongs to G alpha, because note that for F alpha we had this inequality that this left hand side given by the lim sup is greater than 2 alpha, and so since if you have two numbers lambda 1 and lambda 2, and if you add them and if you get greater than 2 alpha, this implies either lambda 1 is greater than alpha or lambda 2 is greater than alpha. So either the first term is greater than alpha or the second term is greater than alpha, which means that if x is in E alpha, then x belongs to either f alpha or g alpha, which is another way of saying that E alpha is contained in the union of f alpha and g alpha, which means that the measure of E alpha is less than or equal to the measure of f alpha plus the measure of g alpha. Now the measure of g alpha is quite easy to estimate by Markov's inequality. So by Markov's inequality, we get that the measure of g alpha is less than or equal to 1 over alpha L1 norm of f minus g. And so this term is actually, so for the second term in the last inequality here, so this term is less than or equal to epsilon by alpha. So this is because this is less than or equal to epsilon, g was chosen to be less than or such that the L1 norm of f minus g is less than or equal to epsilon. So the measure of g alpha is less than or equal to epsilon by alpha. Now the main thing to show is that the measure of f alpha satisfies a similar inequality, and this inequality has a name. This is called the Hardy-Littlewood maximal inequality. Hardy-Littlewood maximal inequality, and it says that the maximal function, so if f is in L1 of R, then the maximal function, so rather I should say that the measure of the set of points in R such that the maximal function of f greater than alpha is less than or equal to 3 over alpha L1 norm of f. So this is a kind of inequality. These are called weak type inequalities, and these are extremely useful in doing analysis when you are trying to measure the variation of this L1 function f when you vary the integral over large intervals, well, the average of the integral values. So because mf is the supremum over h greater than 0, 1 over h x to x plus h ft mod dt. So this is this term that we are taking the supremum of is some kind of average value that the function f takes over large intervals. So this Hardy-Littlewood maximal inequality is giving us the required estimate, because this is nothing but f alpha. So let us suppose that the Hardy-Littlewood maximal inequality holds, and then let us finish the proof. So by Hardy-Littlewood maximal inequality and Markov's inequality, we get that the measure of E alpha, which is less than or equal to measure of f alpha plus measure of g alpha, this is less than or equal to 3 over alpha norm f minus g L1 norm plus 1 over alpha norm of f minus L1 norm of f minus g. So this first term is by Hardy-Littlewood and the second term is by Markov. So then we get this is equal to less than or equal to 4 over alpha times epsilon, and so since alpha is fixed, and epsilon is arbitrary, we get that measure of E alpha equals 0, and this shows the statement for Lebesgue's differentiation theorem. So now we still have to show that this inequality holds. So this inequality 1 holds. So provided 1 holds. So let us go into the details of the proof of the Hardy-Littlewood maximal inequality. So let us see a generalization of our needed result. So we can state this for general RD rather than just the one-dimensional case, and this is again the Hardy-Littlewood maximal function and Hardy-Littlewood maximal inequality. So if you take an L1 function in RD, then you can define the maximal function in a very similar way to what we did earlier. So we are taking in first the integral of mod f over Euclidean balls. So these are Euclidean balls with center x and radius r. So take the integral over such balls, and then you divide by the measure of this Euclidean ball, and then you take the supremum over all positive radius r greater than 0. What you get is called the Hardy-Littlewood maximal function. So this is the Hardy-Littlewood maximal function, and so the statement of this theorem says 3 things. First is that the Hardy-Littlewood maximal function, which is defined as a function from RD with values in C, this is a measurable function. Second is that it is finite almost everywhere in RD, and the third is the Hardy-Littlewood maximal inequality. So this part is the Hardy-Littlewood maximal inequality, which says that the measure of points in RD for which MF, so there should be an x here, MF x greater than alpha is less than or equal to 3 to the power d over alpha times the L1 norm of f. So this is the third part is the main part, the most significant part of this theorem, and in fact 3 implies 2. So 3, we note it in another color, that 3 implies 2, because if you take alpha higher and higher and take the limit as alpha goes to infinity, you get 0 on the right hand side, and if you take the union on the left hand side, you will get the measure of the set of all x such that mfx equals infinity. So in fact this maximal function actually takes values in 0 plus infinity, the extended non-negative reals, because we are taking the absolute value inside the integral. So then the second part makes sense, that the maximal function is finite almost everywhere, and if you take like I said, the limit as alpha goes to infinity on the right hand side of the third part, and the union of all these sets on the left hand side, then you would get exactly part 2. So for part 1, let's do part 1 first. So let's see a proof of this theorem. So for the first part, we have to show that the set A alpha defined as x in Rd such that m of x is greater than alpha is a Borel set, and in fact I make the following claim that, so this is for any alpha positive and finite. So I claim that A alpha is open. So in terms of functions, this is equivalent to saying that mf is a so-called lower semi-continuous function. So this is just a side remark, and it's not important to go into detail of lower semi-continuity and upper semi-continuity. But let's see how to prove that A alpha is open. So let's take x in A alpha. So there exists an R greater than 0 such that 1 over the measure of bxr integral over bxr mod f dm is greater than alpha. So this is by definition of the Hardy-Littlewood maximal function, which is the supremum over all such things. So if the maximal function is greater than alpha, then there exists an R for which this is also greater than alpha by the properties of the supremum. And since the measure of bxr is of the form alpha d times r to the power d, so let me put cd times r to the power d in d dimensions, the volume of a Euclidean ball of radius r is proportional to r to the power d, where cd is an absolute constant, so it does not depend on x or r, absolute positive constant. So this implies that there exists an r prime greater than 0 such that 1 over m measure of bx r prime integral over bx r mod f dm is still greater than alpha. So I am just enlarging, let me have r prime greater than r. I am just enlarging r. So if you enlarge r, so this is nothing but cd times r prime to the power d, and this is nothing but cd times r to the power d. So if you increase r, the value on the left hand side of this inequality will drop because the value of the denominator has increased, but we can find r prime close enough to r such that the value doesn't drop too much and it does not go below or equal to alpha. So this is just by the continuity of this function 1 over r to the power d for positive, strictly positive values of r. So we can find such an r prime such that this holds, and now choose x prime in Rd such that the norm of x prime minus x is less than or equal to r prime minus r. So in that case we will have the ball centered at x with radius r is contained inside the Euclidean ball with center x prime and radius r prime, because if y belongs to bxr, which means that the norm of x minus y is less than or equal to r, and then this implies that the norm of x prime minus y is less than or equal to x prime minus x norm plus norm of x minus y. So this is nothing but r prime minus r plus r, this is r prime, which means that y belongs to the Euclidean ball centered at x prime and with radius r prime. So once we have this, then we get, this implies that, so remember that we started out with this equation. So this, let me write this inequality as 1. So, and let this be 2. So by 2 we get alpha, which is less than 1 over the measure of b x r prime integral bxr mod of f dm, and this is less than 1 over measure of b x prime r prime. So I can just replace here this x here, replace with x prime, because it will not change the measure of the Euclidean ball, because by translation invariance the measures of all these Euclidean balls is independent of x. And secondly, this is less than or equal to b x prime r prime mod f dm. This is by this inclusion of bxr in bx prime r prime. So bxr is included in bx prime r prime, so the integral is bounded above. But on the right side, what we get is, this implies that the supremum over r prime greater than 0, 1 over the measure of bx prime r prime integral over bx x prime r prime mod f dm is greater than alpha, because it is true for r prime, so it is true for all r prime greater than 0, because you are taking the supremum. So if you take the supremum over all r prime greater than 0, this will still hold, this inequality will still hold. And so, but on the left hand side we have mfx prime greater than alpha. So this means that x prime belongs to a alpha, and in fact I could have taken here an open ball around x with radius r prime minus r, and one would still have this chain of inequalities. Here we would have strictly less than or equal to r, but here maybe strictly less than r, but this still holds. And so finally we will get that we have found a Euclidean ball of radius r prime minus r around x, for which any point lying in that Euclidean ball will satisfy mx prime greater than alpha. So this means that a alpha is open. So this proves the first part, and as we noted above that part 3 implies part 2, so it suffices to show only part 3 now. And so this is the most significant part of the proof, and it requires another result which is called Vitali's covering lemma.